Imagine driving across Kansas today, sun-baked, endless, flat to the horizon. Beneath your wheels lie the bones of creatures from an ocean that should not exist. Forget the maps you know. For millions of years, North America was not one continent, but two, split apart by an inland sea nearly a kilometer deep. A sea that isolated its wildlife and gave rise to the most terrifying hunters this continent has ever seen. The geology of this region keeps a secret in plain sight. Beneath the topsoil of the Great Plains, miles of limestone and chalk are packed with the skeletons of mosasaurs and giant, shell-crushing sharks. These are not shore dwellers. They are predators of the deep open water. Yet they are buried in the geographic heart of a continent thousands of miles from any ocean. How do remains of apex marine hunters, capable of roaming vast nautical expanses, end up fossilized in the dirt of a prairie? The answer lies in a fundamental rewrite of the map, one where the geography of the Earth itself underwent a brutal, violent cleavage. To understand how these monsters died here, we have to grasp the mechanics of a rift that shattered the very foundation of the land, forcing a separation so absolute that it turned one biological world into two competing mirrors of itself. But this rift was not just a geographic line on a map, it was a pressure cooker for evolution. This rift was not just a geographic line on a map, it was a pressure cooker for evolution. For 34 million years, this watery corridor tore the heart out of the continent, creating two worlds that never touched. To the west, the rugged, mountain-fringed landmass we call Laramidia began to forge its own destiny, while to the east, the stable, ancient terrain of Appalachia remained isolated. This was not a minor separation. It was a biological experiment on a continental scale. Animals that started as a single population were severed, left to adapt to radically different landscapes, climates, and ecological pressures. In the West, the shifting tectonic landscape created a hothouse for rapid diversification, while the eastern populations found themselves in a forgotten corner, clinging to older, relict lineages that had long since vanished from the rest of the planet. But as these two continents diverged, they carried a hidden timeline of transformation. Why did the Western animals evolve into the giants that would come to define the end of an era, while the Eastern ones remained locked in an older, slower rhythm? This is where the physics of our planet intervened. To understand why this rift became the ultimate driver of extinction and survival, we have to look at the exact moment this greenhouse world began to tilt, and why the clock was ticking the moment these two continents were pushed apart. The planet's thermostat had essentially been stuck on high for millions of years. During this greenhouse interval, spanning roughly 100 to 66 million years ago, the Earth lacked permanent polar ice caps. With that massive volume of frozen water locked away in glaciers, instead residing in the oceans, global sea levels surged to positions we struggle to map on a modern globe. This was a world of sweltering tropical poles and dense carbon-heavy atmospheres. The low-lying interior of North America offered the path of least resistance for this swelling ocean. As the water climbed, it didn't just flood low basins. It exploited the very structural sag of the continent's default, effectively decapitating the landmass. This rising tide was fed by a global system where water depth was not a seasonal fluctuation, but a permanent, dominant feature of the Cretaceous map. Yet, this wasn't merely a passive rising of the waters. Gravity traps formed across the crust, fueled by a specific, violent mechanism beneath the western edge of the continent that forced the ground to buckle downward, inviting the encroaching seas to deepen their hold. We have to look at the subduction of plates to understand how this basin became a gravity-fed sinkhole for the Arctic and Tethys waters. The Pacific Plate's relentless subduction beneath the western margin functioned like a colossal tectonic wedge, forcing a violent downward flexure of the crust. This mechanical strain fueled the Sevier mountain building event, driving the ancestral Rockies upward while simultaneously depressing the interior into a vast, elongated foreland basin. This trough acted as a gravity trap, a massive geological depression that fundamentally redirected continental drainage. The land was not simply sinking, it was being sucked into a vacuum created by its own internal deformation. Across this deepening landscape, the water began an inevitable, dual-pronged migration. From the north, the Arctic waters surged into the basin, carving a path through the low-lying plains. Simultaneously, from the south, a massive marine transgression pushed upward from the Tethys, flooding the embayment that would become the Gulf of Mexico. These two distinct bodies of water were drawn toward the center of the continent by the sheer weight of the subsiding lithosphere, moving steadily along the basin's axis. The tectonic mechanism was unforgiving, deepening the trough to ensure the northern and southern arms would eventually lock together. As the water moved to seal the gap, the scale of the encroaching invasion grew, setting the stage for the definitive collision that would permanently shatter the continent in two. The tectonic pressure finally surrendered to the weight of the encroaching oceans. From the north, the frigid Maori Sea surged downward, carving a path through the yielding sedimentary basin, while from the south, a massive embayment pushed inland from the Proto-Gulf. This was not a slow creep. It was a violent, geologically inevitable union of two hostile waters. At the point of convergence, the two fronts slammed together, drowning the interior plains and severing the land beneath them. The continent was effectively torn in two, creating a permanent watery barrier that forced every living thing into a forced migration toward the coastlines. A once unified geography dissolved into two isolated islands, Laramidia in the west and Appalachia in the east. This was the moment the physical map of the world broke, creating a wilderness defined by water instead of mountain ranges. As the currents stabilized, a massive, silent volume of water occupied the void, hiding secrets that would eventually sink thousands of feet to the dark, oxygen-starved floor. We are left to wonder what sort of abyss grew here once the water hit its peak, and how deep the darkness actually stretched. At its most expansive, the basin plummeted to depths reaching 900 meters. 3,000 feet of crushing, lightless pressure. Stretching 600 miles wide, this was no mere coastal lagoon, but an inland sea with the capacity to swallow entire mountain ranges. Down at these depths, the sun's influence surrendered to a cold, pressurized silence. Massive currents churned through the mid-water, but at the base, the column of water grew stagnant. The weight of the ocean above stifled any circulation reaching the bottom, creating a distinct, hostile environment that defied the biology of the sunlit surface. This brings us to a geological paradox. The sediment layers laid down in this deep water phase present a riddle that has baffled researchers for decades. Why do we find massive, fragile creatures resting in the rock, preserved with such terrifying precision that their smallest bones remain articulated? If scavengers had been present on the seafloor, these skeletons should have been scattered and shredded long ago. Instead, we are looking at a system that lacked the basic requirements for life to survive at the bottom. But what exactly was happening in that darkness? And how did a lack of oxygen serve as a trap for the apex predators of the surface? The answer lies in the chemistry of the abyss itself. The seaway was hemmed in by tectonic rises, causing deep water circulation to stall. Oxygen levels plummeted to zero. In this anoxic tomb, the usual scavengers, the worms, crustaceans, and bacteria that normally strip a carcass to bone, simply could not survive. When a creature died at the surface and drifted down, it fell into a sterile, toxic void. It did not rot. It settled into the fine, lime-rich mud of the seafloor, effectively buffered against decay. Layers of chalk and shale blanketed these remains, sealing them in a geologic vault. Because the bottom was a graveyard of stagnant chemistry, we find skin impressions, stomach contents, and entire skeletons in poses that appear frozen in motion, as if the water turned to stone. This lack of biological interference preserved intimate details that would have been scrubbed away in any other environment. But while this oxygen-starved floor provides our clearest window into the past, it masks a hidden complexity. We often categorize these chalk beds as the byproduct of a stagnant, lonely pool. Yet the fossils buried here suggest an ecosystem far more vibrant and tiered than the label of a simple basin implies. If this was a dead zone, how did such a lethal environment sustain a food web so complex it pushed marine predators to the absolute limit of their evolutionary design? The water column became a vertical gauntlet, forcing distinct species to carve out specific niches to survive. While the seafloor remained a tomb, the sun-drenched upper reaches turned into an arena for high-stakes competition. Light-seeking hunters and those built for the dim, mid-water gloom occupied separate strata, creating a tiered reality where every cubic meter of water was contested. This vertical confinement left prey with nowhere to flee, forcing predators to develop specialized tactics for pursuit and ambush. The fossil record reveals a rapid, aggressive divergence in body plans. Creatures either hardened into armored, shell-crushing specialists or elongated into lethal, high-speed machines. As geologists peel back the shale, the evidence confirms that this ocean was governed by a brutal hierarchy of teeth and speed. Some species stayed locked in the sunlit surface to patrol for smaller fish, while others specialized for the crushing pressures and darkness of the deep. Yet, one predator refused to be restricted to a single zone. Its fossils suggest a creature whose sheer size and skeletal mass allowed it to command every layer of the seaway at will, turning the entire water column into a private hunting ground. To understand how such a monster maintained its grip on 1,000 miles of inland ocean, we must look at the weaponized anatomy that made it the undisputed master of this fractured world. At the top of this lethal food chain prowled Tylosaurus, a leviathan reaching 14 meters in length. It was a kinetic battery of muscle and bone, built to dominate the open water. Its skull, reinforced by a massive, fused premaxillary tip, functioned as a living battering ram. This was not a slow-moving creature. Its elongated, serpentine tail powered explosive bursts of speed, allowing it to transition from a dead drift to a terminal strike in seconds. Mosasaurus and its kin shared this high-performance architecture, turning the stagnant, oxygen-starved depths into a stage for relentless, high-stakes hunting. Their sheer size and predatory efficiency placed them at the absolute pinnacle of the Cretaceous ecosystem. Yet, the fossil record preserved in the Pierre Shale reveals that these lizards were not the only threats moving through the water column. A second, entirely different predatory design occupied these same depths, operating on a radical architecture that prioritized extreme reach over the heavy-hitting profile of the mosasaurs. This biological divergence meant that while the giant lizards ruled through crushing force, another, more delicate shadow began to haunt the middle water levels. This sudden shift in anatomical strategy leaves us with a critical, unanswered question. How did such a fragile, long-necked hunter survive alongside these absolute masters of the deep? The answer lies in the evolution of the elasmosaur. Unlike the brute, high-speed aggression of the mosasaurs, creatures like Styxosaurus were the masters of concealment and patience. They evolved a body plan that defied standard predatory logic, a neck that could extend nearly 7 meters, making up half of their total length. While the apex lizards relied on massive kinetic force to shatter bones, the elasmosaur utilized a strike-from-distance strategy. They ghosted through the intermediate layers of the water column, their tiny heads darting out with sudden, fluid precision to snag small prey before the massive predators even registered their presence. This was vertical niche partitioning taken to its anatomical extreme. By occupying this silent, deep-water middle ground, these long-necked hunters avoided direct physical confrontation with the mosasaurs, effectively carving out a private, terrifying domain within the same shared ocean. Yet, this specialization left them vulnerable to a different kind of threat. When these hunters looked up from the depths, they faced a surface world teeming with its own rapid, high-intensity killers. The water above was not empty. It was a high-stakes hunting ground, and something larger and faster was already watching from the sun-drenched layers near the waves. These warm, sun-drenched layers belonged to the Xiphactinus. Measuring 5 meters long, this bony fish was an explosive, high-velocity missile. Its torpedo-shaped frame allowed for sudden, violent bursts of speed, transforming the surface into a gauntlet of ambush. Lined with serrated, blade-like teeth, its jaw was engineered to lock onto prey with terrifying finality. While the giant reptiles held the dark, oxygen-starved floor, the Xiphactinus enforced a relentless, predatory pace near the waves. It was the chaotic face of the Seaway, patrolling the carbonate-rich water with an impunity that left no margin for error. Yet, this high-speed dominance was fragile. The fossil record reveals that this shallow water terror was far from the only threat in the water column. Beneath the churning surface, the biological hierarchy was defined by far more complex strategies. A different class of hunter was operating with mechanics that the Xiphactinus simply could not match, carving out lethal ranges that forced this apex fish to contend with sharper competition. The balance of power was shifting as specialized predators prowled the same geographic space, encountering a shark population that held the oceanic hierarchy in an entirely different, more brutal grip. Cretoxyrhina evolved to view even the largest marine reptiles as prey. Measuring 7 meters, this active hunter was built for high-velocity strikes. Its serrated, dense teeth functioned like a serrated blade, engineered to slice through thick hide and bone with clinical efficiency. On the fossilized remains of mosasaurs and plesiosaurs, forensic evidence confirms the nature of these lethal encounters. Deep puncture marks and embedded tooth fragments prove that Cretoxyrhina did not merely patrol the periphery. It actively hunted the seaway's apex reptilians. This predator could sever a mosasaur's tail or strike a swimming plesiosaur, forcing a total reordering of the open water hierarchy. While Cretoxyrhina stalked the living, Squalicorax maintained the order of the dead. This robust, opportunistic shark acted as the ecosystem's primary scavenger, feeding on the remains left in the wake of the larger predators. Squalicorax processed the carcasses drifting through the oxygen-depleted zones, ensuring biological energy remained in constant circulation. Yet, this intense competition left a massive, untapped food source entirely untouched. The seafloor was carpeted in thick, calcified armor that neither the slashing teeth of the Ginsu shark nor the opportunistic jaws of Squalicorax could penetrate. A hidden, heavy-duty bounty waited in the silt, requiring an entirely different tool to crack. This leads us to P.I. Codus. Stretching up to 10 meters, this shark was an anatomical outlier, trading serrated blades for a dense, pavement-like mosaic of crushing plates. These flat teeth formed a powerful battery specifically evolved to withstand the immense force required to shatter the thick, calcified shells of inoceramid clams and massive ammonites that carpeted the seafloor. While predators like the Ginsu shark patrolled the surface, P.T.Y. Codus ruled the benthos as a dedicated durophage. It turned the sediment-rich bottom into a private banquet, utilizing gargantuan jaw strength to harvest armored invertebrates that other hunters simply could not process. This specialization granted T.I. Codus total jurisdiction over the deep, silt-heavy zone, effectively mining the seafloor for food that had remained untouchable for millions of years. Yet, the pressure of this relentless consumption forced a shift in the local ecosystem. As these seafloor resources were scraped clean by the persistent, heavy-duty jaws of T.I. Codus, smaller, vulnerable organisms were pushed out of their benthic sanctuaries and into the perilous open water. They drifted upward, away from the safety of the mud, directly into the path of an even larger, more resilient shadow gliding through the current. A creature of such scale that its very presence would mark a turning point for everything swimming in the seaway. This silhouette belongs to Archelon. Measuring 4 meters from flipper to flipper, this is the largest turtle to ever inhabit the Earth. It does not possess the speed of the mosasaur or the predatory bite of the shark, yet it occupies an untouchable position in the hierarchy of the seaway. Its size is a shield, a biological fortress built against the hunger of the open water. While other creatures must constantly fight to stay at the top of the food chain, Archelon thrives by simple, massive durability. Skeletal remains pulled from the Pierre Shale of South Dakota reveal an animal that spent its life patrolling the columns of the Central Sea, seemingly oblivious to the chaos below. Its shell, reaching 13 feet across, provides enough protection to defy the smaller predators that haunt the surface, yet even this armor is only a temporary defense. The sheer presence of such giants raises a persistent, gnawing question about the stability of the entire ecosystem. If the waters are rich enough to support creatures of this magnitude, what exactly is fueling their growth? The answer lies further down the strata, tucked away in layers of sediment that hold the remains of organisms far more alien than a turtle. A hidden, invertebrate world of impossible dimensions that provided the foundation for everything else to survive. Beneath those hunting grounds, the seafloor was far from a barren wasteland. It was carpeted by life on a scale that defies standard biology. Consider the inoceramids, massive, bivalve mollusks that anchored themselves to the silt. Some reached up to 3 meters in width, flat, organic plates covering the substrate like a living mosaic. These were not mere shells. They were the primary builders of the ecosystem, their calcified remains accumulating into the very limestone that now defines the Kansas landscape. Swimming through the shadows cast by these bivalves were the cephalopods, ammonites like Parapuzosia, which pushed the limits of invertebrate growth. These creatures grew to the size of a car, their spiraled chambers navigating the nutrient-rich currents as they preyed on smaller squid-like belemnites. In this high-productivity zone, where the water remained warm and the seafloor was saturated with the waste of 1,000 generations, these shelled giants thrived. They provided the steady, reliable protein source that allowed the specialized shell crushers to evolve into the apex forms we see in the record. But this bounty was not exclusive to the water. As these massive shells and bodies drifted, they created a constant supply of energy that didn't just fuel the swimmers. It provided a persistent, reliable target for those that looked down from the clouds. These aerial sentinels were the pteranodons, creatures defined by massive wingspans that allowed them to dominate the thermals above the sea. They were not mere transients. They were specialized hunters of the open surface, built for a specific, high-stakes trade. Their skulls, elongated and topped with distinct aerodynamic crests, functioned as precision tools for scanning the water for the flicker of a school of fish or the surface burst of a small predator. Unlike the heavy reptilian carnivores lurking in the depths, Pteranodon relied on speed and reach, snatching prey directly from the top few feet of the water column, before lifting back into the updrafts. They were as much a part of the seaway's anatomy as the mosasaurs and the shell-crushing sharks. Fossil beds in the Kansas chalk preserve them in eerie detail, sometimes with their wings folded, sometimes with their long, toothless beaks still angled toward a meal they would never finish. But while these pterosaurs owned the wind, they shared their hunting grounds with something far more grounded and specialized. They faced competition from a different class of predator, one that had traded the ability to fly for the dangerous high-energy life of a deep-water diver. This rival design, a bird that had abandoned the sky to hunt in the darkness of the sea, would soon change the way the ecosystem functioned entirely. Hesperornis was a specialized torpedo, a flightless hunter standing nearly 2 meters tall, with a serrated, needle-toothed beak and powerful, rear-facing legs, it abandoned the sky to master deep currents. By tucking vestigial wings against a sleek, elongated body, it could drive through the dark, oxygen-starved water, cornering schools of smaller fish that thrived in the mid-water column. Its fossils, entombed in the same chalk that holds the sea's leviathans, document an avian species that became a ruthless specialist of the abyss. Above the waves, Ichthyornis took a divergent path, keeping its wings agile while retaining the ancestral teeth of its reptilian kin. These were high-speed interceptors, dive-bombing the surface to snatch prey from the water's edge. These birds bridged the gap between the shoreline and the open sea, linking the sky to the same rigid hierarchy that governed the marine giants. They occupied the margins where heavier hunters could not reach, yet the pressure was constant. Every creature, from the avian diver to the surface-skimming predator, lived in the shadow of a lethal encounter. The density of predators meant that death was often instantaneous, leaving behind a frozen, frantic snapshot of the daily violence that defined these waters. A violent secret that was preserved for millions of years, locked in a single, gut-wrenching piece of evidence. The most jarring evidence of this constant predation is the specimen known as the fish. Within a fish, unearthed from the Kansas chalk, this Xiphactinus serves as a forensic capture of the extreme ecological pressure that governed these waters. It shows a 5-meter-long predator with a stomach so distended it suggests the animal died from the internal trauma of a meal too massive to process. Tucked neatly within the ribcage of the killer lies a smaller Gillicus, swallowed whole just moments before both fish sank into the oxygen-starved floor. The specimen was locked into the accumulating limestone, perfectly articulated in its final, frantic effort. Every scale and the precise position of the prey demonstrate the violent efficiency required to command the mid-water column. Yet, these fossils present a geographic contradiction. They sit embedded in arid, sun-drenched plains, thousands of miles from any modern coast. The presence of such marine giants in the heart of the continent demands an explanation for how an entire ocean could simply vanish. To see the scale of this loss, we must turn to the landscape itself, where the very foundations of the prairie reveal the truth of the seabed. To find the heartbeat of this vanished world, look to the wind-swept plains of western Kansas. Here, rising abruptly from the flat agricultural horizon, stand the Monument Rocks. These chalk spires are not mere geologic curiosities. They are the literal seafloor, lifted and exposed by time. When you run your hand across their weathered face, you are touching fine-grained carbonate mud that settled in the deep, oxygen-starved dark of the Cretaceous. This is Niobrara chalk, a layer forged from the microscopic skeletal remains of billions of plankton, compressed under the weight of an ocean that once spanned 2,000 miles. Every fissure in these pillars contains the ghost of an environment defined by extremes, a suffocating, anoxic bottom layer that acted as a chemical shield, locking entire skeletons into stone before scavengers could tear them apart. Yet, as geologists trace these chalk beds across the state, the story of the seabed shifts toward the shoreline. The deep water stillness gives way to evidence of a much more turbulent, chaotic borderland, where the open water slammed against a restless, rising coast. As the sediments change, so does the nature of the danger. Out in the deep, the threats were swift, gill-bearing predators, but near the mudflats and the ancient river deltas, a terrifying, massive jaws-driven terror was evolving to hunt in the shallows. This is where the massive apex crocodilian Deinosuchus reigned. While the mosasaurs and sharks ruled the dark central depths of the basin, this 10 to 12 meter behemoth occupied a specialized, violent territories tour along the coastlines. Its skull, capable of crushing force, was not designed for the open water pursuit of swift fish, but for ambushing prey that ventured into the murky, brackish river deltas, where the land met the sea. The geography of the coast provided the perfect concealment for a predator of this mass. It patrolled the shallows, waiting for the terrestrial fauna, the dinosaurs of Laramidia, to drink from the edge of the world. Evolution carved Deinosuchus into a niche that bridged the land and the interior sea, creating a deadly barrier that kept the deep-water hunters and the land dwellers separated by an iron-fisted, semi-aquatic patrol. Yet, the physical bones of these giants, just like the remains of their oceanic rivals, eventually settled into the same mud, waiting for someone to peel back the layers of time. The question remains, how did humanity first unearth these scattered monumental pieces of a sunken world? And what kind of madness drove the 19th century explorers who finally realized what they were looking at? The answer lay in the high-stakes obsession of two men, Othniel Charles Marsh and Edward Drinker Cope. By the 1870s, the American West became a battleground for scientific legacy. As the Transcontinental Railroad penetrated the arid interior, these bitter rivals pushed their crews into the remote Kansas chalk beds. Their race was defined by scorched earth tactics. Hunters were often instructed to smash specimens rather than allow a competitor to catalog a new species. Yet, through this toxic fervor, they unearthed thousands of massive, intact fossils perfectly preserved by that ancient, oxygen-starved seafloor. They were the first to grasp that these bleached white cliffs were the skeletal remains of a vast, submerged graveyard. As these men fixated on the violent anatomy of the deep, they unknowingly charted the edges of a fractured world. This sea functioned as a biological gatekeeper, forcing a distinct evolutionary path for every living thing trapped on either side of the rift. If marine predators were the byproduct of this divided planet, the terrestrial life isolated on Laramidia and Appalachia faced a more radical transformation. The water did more than separate the land. It acted as a crucible that dictated the path of life across the continent, forcing two separate evolutions to diverge in silence. On the narrow western strip of Laramidia, the tectonic squeeze and the encroaching saltwater turned the landscape into a biological pressure cooker. Isolated from the eastern Appalachia landmass, the dinosaurs here were forced into a unique, rapid evolutionary experiment. In the shadow of the rising Sevier Mountains, the fauna shifted. The massive, crushing jaws of the tyrannosaurids, the complex, defensive armor of the horned ceratopsians, and the booming herds of hadrosaurs emerged as the products of this cramped western refuge. Meanwhile, Appalachia became a forgotten corner of the Cretaceous. Cut off by the deep water, its ecosystem remained largely shielded from the sweeping biological turnover happening to the west, preserving older, relict lineages that had already vanished from the rest of the world. It was a continent cleaved into two distinct theaters of existence, with the seaway functioning as an impassable barrier to gene flow. How could two halves of a single landmass sustain such radically different evolutionary paths for millions of years? And as the sea held them apart, deep beneath the surface of the continent, the very crust began to shift in a way that threatened to rewrite the map once more. The forces that had carved out the seaway were already losing their grip. As the tectonic machine that built the mountains began its final violent push, the tectonic geometry of the western margin shifted as the subducting slab flattened and shoved massive compressive forces hundreds of miles inland. This was the birth of the Laramide orogeny. Deep beneath the crust, the lithosphere buckled, forcing the ancestral Rockies to surge upward, where a massive gravity trap once kept the landscape sunken beneath the waves. The crust now heaved in a violent upward arc. This was not a slow settling. It was a structural inversion that shattered the basin's integrity. The seafloor, once a haven for stable, horizontal sediment accumulation, was folded, fractured, and tilted toward the horizon. As the central corridor rose, the ocean's depth could no longer be sustained. The tectonic floor effectively buckled against its own basin, forcing the water to shed its volume. The massive, oxygen-starved reservoirs were violently displaced, drained by the tectonic heave of the rising land. The Central Sea, which had served as a barrier for millions of years, now found its northern and southern connections severed. What was once a unified, deep-water domain began to fracture into shrinking, disjointed pools. The Earth was reclaiming its territory, and the water, deprived of its basin, had nowhere left to go. The regression had begun, and the clock was now running on the last of the open water. The shallow marine retreat was not an overnight evaporation, but a jagged, retreating collapse. As the Laramide orogeny forced the crust to buckle and rise, the basin floor, once an oxygen-starved graveyard of silent leviathans, tilted toward the south. The Arctic connection was severed first, leaving the remaining water to pool in a shrinking, muddying corridor known as the Pierre Seaway. We can trace this death rattle in the sediment itself. The deep-sea Pierre Shale gives way to coarser sands and terrestrial clays, a physical diary of a rising shore. Massive lagoons formed and vanished, trapping isolated populations of marine life in shrinking hypersaline pockets. The great interior ocean was being squeezed out like water from a sponge, forced through the narrow neck of the ancestral Mississippi embayment toward the Gulf. Yet, as the shoreline retreated, the true biological cost of this drainage began to emerge. The land was not just drying, it was becoming a bridge. For 30 million years, the western shores of Laramidia and the eastern coasts of Appalachia had been separated by a barrier that defined their very existence. Now, that filter was dissolving. As the tide retreated, the two disparate worlds began to drift back into each other, setting the stage for an ecological collision that would rewrite the map of North American life forever. As these two ecosystems collided, the evolutionary path of North America shifted into total chaos. For millions of years, Laramidia had acted as an incubator for specialized giants, refining lineages of ceratopsians and massive theropods that had no analog in the East. Appalachia had functioned as a relic archive, preserving archaic, slower-paced lineages that remained largely unchanged while their western cousins transformed. As the land bridges reconnected, these separated genetic blueprints were forced into immediate, brutal competition. The specialists of the West. Dinosaurs engineered for high-intensity grazing and predatory speed poured across the emerging mudflats, encountering competitors they had not seen in an epoch. Native eastern populations found themselves overwhelmed by these arrivals, while Western migrants struggled to adapt to an unfamiliar climate and the dense, swampy terrain of the Appalachian heartland. It was a rapid, violent shifting of the natural order that favored the most mobile, generalist survivors. The stage was being cleared for a catastrophe that would render these hard-won victories irrelevant, as the last of the seawater drained into the growing gaps between the emerging Rockies. A far deeper, more existential mystery began to take shape. When the environment that defined an entire era vanished, why did some lineages endure while others vanished with the sea? The regression forced a brutal census of biological viability. Specialized hunters, engineered over millions of years for cold, deep-water columns, found themselves trapped in an evolutionary dead end. Their anatomy, honed for the precise pressures of a 1,000-meter basin, could not pivot as the water retreated. The great mosasaurs and the giant ammonites, once masters of an open sea, were tethered to a marine habitat that ceased to exist. They were casualties of their own hyper-adaptation, locked into niches that were drying into dust. Conversely, the generalists, creatures that straddled the margins, capable of moving between coastal shallows and emerging river systems, found a chaotic opportunity. The drain of the seaway left behind vast, unstable frontiers. Species that had been physically segregated for eons by the water barrier suddenly collided on the muddy banks of a shrinking coastline. This was a total, violent reconfiguration of the food chain, a fragile instability that left the continent exposed. By the time the Chicxulub impact arrived to finish this broken landscape, the seaway was already a fading ghost. And then the asteroid, the Chicxulub impact, hit a system already gasping for air. By the time the skies darkened, the Interior Seaway had retreated into a shallow, stagnant ghost of its former self. Regression had forced the apex predators into a tightening trap as the basin drained and the continental crust buckled under the final, crushing phases of the Laramide orogeny. Species that had occupied deep, open water for tens of millions of years found their ranges replaced by expanding mudflats and inland streams. For the mosasaurs, the seabed was literally rising to meet the sky. The contraction meant that by 66 million years ago, the specialized niches of the Niobrara were gone, leaving only generalists capable of shifting toward emerging coastal environments. When the firestorm arrived, there were no deep-water sanctuaries left. We are now left with a landscape that holds the fragmented evidence of this retreat, etched into the strata beneath our feet. Yet, the physical evidence remains buried in a puzzle of scattered rock layers. To grasp the true scale of this collapse, we must look at how the Earth itself preserves the retreat. How do geologists track the exact pulse of a disappearing ocean? And can we reconstruct the final, desperate shorelines of a sea that vanished into the crust millions of years before humanity ever walked these plains? That requires us to follow the literal footprints of the water. That requires us to follow the literal footprints of the water. Geologists perform this reconstruction by mapping the transition from marine limestone to terrestrial sediment across the states that flank the current geography. Each outcrop of Niobrara chalk is a forensic marker, a spatial anchor point that tells them exactly how far the sea encroached at a specific moment. By measuring the thickness and chemical composition of the Pierre Shale as it thins against the rising slope of the emerging Rocky Mountains, they can plot the contraction of the shoreline with startling precision. It is a puzzle of subtractive geography. They connect these isolated fossil beds like dots on a chart to define the retreating tidal edge. They track the chemical signatures of oxygen-poor bottom waters, identifying where the oxygen levels first spiked and the seafloor life returned, marking the death of the deep water basin. This mapping reveals a map of an ocean that no longer exists, pinned down to the square mile. The data is hidden in the very ground beneath the towns and farms that now occupy the region. But these rock units hold a secondary secret. The reason why the central United States possesses such a distinctive, sweeping flatness. The reason the landscape lacks the rugged complexity found elsewhere lies not just in the drainage of the water, but in the long-term burial of the structures that were there before. The seafloor acted as a massive, near motionless settling pond. Over 34 million years, currents slowed as they entered the basin, allowing fine-grained particles of calcium carbonate and microscopic plankton to drift, undisturbed by the turbulence of open ocean waves. This continuous rain of chalky debris draped over every pre-existing hill and valley, filling irregularities like fluid in a mold. As the basin sagged under its own weight, the seafloor was smoothed, layer by uniform layer. The massive pressure of the water column compacted these sediments into the rigid Niobrara chalk and Pierre Shale foundations that now anchor the mid-continent. The Great Plains do not merely occupy a former seabed. They are a direct product of its patient, persistent burial process. This methodical paving of the crust, however, was only one phase of the basin's life. The story of this ocean is defined by the sharp, irreconcilable contrast between this rhythmic, quiet deposition and the sudden, wrenching tectonic force that eventually shattered the environment. The sea's birth and death were driven by wildly different engines, a fundamental tension between the steady accumulation of geologic time and the violent, crushing ambition of mountains. The slow subsidence of the Foreland Basin was a structural trap that captured the sea, but its erasure required a pivot in the planetary architecture. While the inundation was a consequence of tectonic down-warping, the draining was fueled by the rise of the Laramide orogeny. As the lithosphere began to buckle and thicken, the floor of the basin was literally forced upward, reclaiming the territory from the water. This was not a sudden vanishing act, but a protracted death of a world. The connection to the Arctic was the first casualty, severed as the northern gateway closed. The sea became a shrinking, terminal remnant, a shallowing lagoon trapped between the rising Rockies and the Appalachian highlands. As the surface area retracted, the chemistry of the water shifted. The oxygen-starved deep basins, which had acted as a protective vault for the biological record, were physically hoisted into the atmosphere. Erosion began to dismantle what the sediments had spent millions of years constructing. The Pierre Shale, once a quiet benthic tomb, was broken by the same forces that built the mountains, turning the soft clay into the exposed badlands of the Dakota Plains. Now, the final mystery remains. Why do the remnants of this aquatic death trap lie scattered across the dust of the high desert? And how did these creatures end up thousands of miles from the modern coastline? Those skeletons don't lie in the dust of Kansas by accident. They are there because the seafloor itself has migrated. The tectonic violence of the Laramide orogeny did more than just drain the water. It acted as a massive geological conveyor belt. As the crust buckled and the Rockies surged upward, the entire floor of the seaway was physically tilted, lifted, and pushed eastward. What was once the dark, oxygen-starved floor of a basin thousands of feet deep is now the foundation of the high plains. The fossils of a Tylosaurus once pinned in the soft, anaerobic mud of the Niobrara chalk remained protected beneath layers of sediment, slowly rising along with the continental crust. We aren't finding these monsters because they swam into the interior. We are finding them because the interior has been turned inside out. The very ground that supported the deep water hierarchy of the Cretaceous is now the stage for the modern prairie, locking these marine hunters into the rock itself, waiting for the rain to strip away the shale and reveal the ghost of a world that vanished long before we ever arrived. The physical gulf between Laramidia and Appalachia was never just a shoreline. It was an evolutionary forge. Confined to the west, Laramidia functioned as a pressurized lab. Limited space and volatile resources pushed life toward intense specialization, accelerating the rise of horned ceratopsians and massive, hyper-aggressive theropods. Meanwhile, Appalachia acted as a remote sanctuary. Its stable geography allowed relict lineages, ancient groups long vanished from the restless West, to persist undisturbed. For millions of years, the Seaway locked these worlds in a state of rigid genetic quarantine. When the Laramide orogeny finally inverted the basin and the water retreated, that barrier collapsed. East and west slammed back together, sparking a violent ecological collision. Appalachian endemics were suddenly forced to compete with the relentless, evolved specialists surging from the west. It was not a balanced integration, but a purge. The reunified continent favored the resilient, adaptable generalists. This mass reshuffling turned two static evolutionary tracks into one chaotic, unified field of competition, setting the stage for the final, desperate chapters of the Cretaceous before the world changed forever. As the waters drained, the Seaway's specialized titans faced an impossible retreat. For the massive ammonites and the apex mosasaurs, that 3,000-foot water column was a biological mandate. They were locked into narrow, high-efficiency niches. When the basins buckled and fractured, those environments vanished entirely. They were not merely outcompeted. They were physically severed from the dark, stable, anoxic conditions their physiology demanded. With nowhere to migrate, the specialists hit a terminal wall. Survival favored the generalists. Smaller sharks and resilient coastal scavengers could pivot, enduring the fluctuating salinity of fragmented, shrinking lagoons. Extinction follows a ruthless rule. When niche stability shatters, the specialist vanishes first. The regression acted as a violent sieve, filtering out the complex predators that required vast, deep-water volume to survive. By the time the final remnants reached the Gulf, only those capable of navigating the chaos of a drying, fragmenting interior endured. This massive turnover proved that even the most formidable hunters are vulnerable when the foundation of their world is in flux. If an ocean could rise, bisect a continent, and simply cease to be, we are forced to wonder about the permanence of the coastlines we stand upon today. We are standing on a temporary crust, a thin veneer layered over a planet in constant motion. The same deep-time forces that bowed the continent and flooded the interior remain active, hidden in the slow creep of tectonic plates and the rise of mountain chains. Our current geography is a mere snapshot in a cycle that never truly halts. The Great Plains, once an ocean floor, now sit thousands of feet above sea level, forced upward by the same lithospheric buckling that ended the Cretaceous Sea. We see this persistent instability in the seismic zones along our coasts, where subduction continues to pull at the edges of the land. The transition from open water to arid prairie confirms that the sea levels we take for granted are subject to the same tectonic and atmospheric shifts that once erased a massive maritime world. Every spire of chalk in Kansas acts as a silent index, a reminder that the continent we call permanent is merely waiting for the next turn of the tectonic wheel. The ocean did not vanish because it was defeated. It left because the planet moved on. That process is not over. It is only patient, waiting for the next tremor to redefine the map. That process is not over. It is only patient, waiting for the next tremor to redefine the map. Recovering the ghost of this ocean requires you to become a forensic detective of the local landscape. When you stand on the high plains, you are traversing an ancient sediment trap that once accumulated immense depths of carbonate ooze. Look closely at the walls of a road cut or the weathered face of a limestone outcrop in Kansas or Nebraska. You are seeing the compressed remains of billions of microscopic marine organisms that once fell through that stagnant, oxygen-starved water column. Search for the distinctive, paper-thin white flakes of chalk or the telltale iron staining of a fossilized ammonite shell. These markers define a world that vanished in a geologic blink. Tectonic plates drift and seas rise, constantly rearranging the geography of the surface. By identifying the characteristic layers of the Pierre Shale or the Niobrara Formation in your own backyard, you read the final, brutal chapter of the Cretaceous. The Western Interior Seaway exists today as the ground supporting your home, proving a continent remains only as stable as the tectonic forces beneath its skin. Watch the stones. Every layer records the surge of an ocean that once tore North America apart, and every cliffside displays a map of a landscape still being rewritten by the earth beneath your feet.